Okay, underneath the umbrella of continuous distributions, we encounter the normal distribution. In statistics, this is our bread and butter. We do a lot of comparisons to this, so it's helpful to get a good understanding of as far as what makes a normal distribution normal. This is what we consider to be a bell-shaped curve, where there's a hump in the middle and some observations that are extreme on both the left and the right end. We typically refer to a normal distribution in terms of its mean and standard deviation. And we have something called transition points at every standard deviation away from the mean of that. We'll look at examples of this. This is where our geometry skills are going to kind of leave us, and we're going to use some calculator skills and look up some information from the book. Let me kind of start by giving you a sense of what makes a normal model normal, kind of illustrating what this means is that standard deviation increases or decreases. So in your calculator, if you go to right above the variable menu, the vars menu, you see this little tiny thing called DISTR, distributions. And if we arrow over to draw, we see something called shade norm. Okay, so what I'm going to do is I'm going to tell the calculator, I want you to shade from -3 to +3, and I'm going to keep this the standard deviation, the mean of 0 and the standard deviation of 1. This is called our standard normal curve. And then I'm just going to have the calculator draw that for me. And this is, again, what we consider textbook example of a normal distribution. Nice hump there in the middle at 0. And what I'm going to do is I'm going to increase the standard deviation of this curve and just notice the change. So I'm just going to go right back to shade norm. We'll keep the upper and lower the same, mean of 0, but we're going to up the standard deviation to 1.5. And then when I draw it, hopefully we'll notice something different. Notice it's going to draw right on top of it there. And kind of hard to tell, but it was lower there. Let me go back and do that again. Let me switch colors on us. So -3 to 3, 1.5. Let me switch it to that, to red. Your calculator might not be able to do that, but so as it's drawing that in, you can see that when the standard deviation increased, the curve got flatter, and we're going to do that one more time, but let me decrease the standard deviation here. And again, right now I just want to give us a sense as to what the standard deviation is doing to our normal model. So I'm going to go -3 to 3, and mean is the same. We're going to make this 0.5, and then let's switch it to black. And then when I graph that, just kind of notice what happens. The 3 different color schemes there. So notice it got skinnier, taller and thinner, as they say. So the standard deviation impacts, when compared to a standard deviation of 0 and 1, sort of impacts how the graph views. Increases, the curve gets flatter and it's more spread out. Decreases, it gets taller and thinner. Well, why do we care? Some places that the normal model tends to have relevancy, things like newborn baby, height, weight, college entrance exam scores, intelligence scores, pretty much a lot of processes where we have a single expected value and there's very few extreme good and bad cases we consider to be a normal model. Okay, so here's kind of a graph to kind of think about some of those earlier concepts and kind of tie them together. We've got 2 normal models on top of each other, curve A and curve B. Start with the first question. Does it appear they have the same mean? And if so, what is it? Well, they both look like they're centered right above this line. And if I count over 1, 2, 3, 4, 5, 6, it looks like the mean's right there at 6. Okay. Which of the two curves has a standard deviation of 3 versus 1? Well, keep in mind, the larger the standard deviation, the flatter the curve, and the smaller standard deviation, the taller the curve. So with that said, kind of filling our information there, we get standard deviation of 3 is curve B, and standard deviation of 1 is curve A. Now, we're actually not strangers to the normal model. We've looked at the empirical rule before. That's the 68, 95, and 99.7 rule. And again, just to remind you, within inside those three statements, and this is another illustration of those transition values there. So we start adding standard deviations. So the middle, if I go one standard deviation away from the mean, I get, we said 68% of the data should be within those values. So if I chop that up using symmetry, I get 34% on one side and 34% on the other. Then we had 95% for the other part. And again, using symmetry, I can get these other two percents to sort of balance out. So it's 13.5 on each end to get the other amount. And then the 99.7 is where I can get that to justify the 2.35%. So assuming we're looking at this type of normal model, we can use symmetry to figure out probabilities. So say we're told that a group of male students is normally distributed with 71 inches and standard deviation of 2.5. What's the probability that the height of a randomly selected male student is more than 73.5? Well, what's the significance of 73.5 and 71 and 2.5? Okay. Well, this line right here, if I add 2.5 to 71, I get 73.5. So that 73.5 is relevant when we're talking about one standard deviation away. So at one standard deviation away, I get 68% from it. It's kind of going back up here. I'm looking at this line right here, and we're asked about it being greater than this. So one thing I can do is I can just add up all the percents to calculate that. So we want this part of our curve that we're trying to figure out. So I could just add them up and using that previous chart, or just taking the fact that using symmetry, I know that this is 68%, which means the other two sides have to be 32, and I want just the upper piece. So 32 divided by 2 is 16. So 16% of the heights are going to be larger than that particular value. Okay. Now, let's give a name to this. When we have a mean of 0 and a standard deviation of 1, this is what's called the standard normal density curve. We actually throw the word standard in front, so standard normal. And the great part about this is now we get to talk about z-scores, and the formula to calculate a z-score, that's why we put a z there, is our observation minus the mean divided by the standard deviation. We do a lot with this. As a matter of fact, I just want to come right out. I expect us just to know how to calculate that z-score for a standard normal curve. X minus mu divided by sigma. Now, when we are trying to calculate a given probability within these normal models, we're going to follow a four-step process. We're going to first write out the probability statement. We're going to draw a picture to illustrate that particular probability statement. Then we'll calculate the z-score based on the parameters we're given. And then at that point, we'll look it up, the probability for the z-score, either based on a table or more likely we'll use a calculator, and I'll kind of show you the relevant calculator skill here when we get there. So I want to dive into an example of illustrating these four steps here. So we're told that the lifetime of a certain type of battery is normally distributed with a mean of 200 hours and a standard deviation of 15 hours. And the question is, what proportion of these batteries can we expect to last less than 220 hours? So they tell us that on average, the mean, about 200 hours, what percent of the time are they going to be actually less than 220? Okay, so we start off by writing our probability statement, which is the probability of an observation being, so that capital X, less than 220. Then I'm going to draw a picture of what this is represented by. So we're going to sketch a normal model, and the reason why I picked a normal model is it told us in the problem it was normally distributed. Earlier we've seen uniform model, and that would be we sketch a rectangle. But in this case it's a normal, so we draw in the bell curve there. And I'm interested in less than 220, which I know is larger than the mean. So I know my curve's got to look like this. I don't have any numbers in there, but I know it's got to look, looking at this shaded region, which is what I want to find the probability of the area of that particular piece. Then we're going to find the z-score. So the observation, the observed is 220, the expected is 200, and the standard deviation is 15. So calculate that to be about 1.33. Okay, so at this point we're going to calculate the probability or p-value of this particular scenario. And we could go look it up in a table in the book where we just look up the z-score and look up the probability of less than it. I'm going to actually show you a calculator skill related to it. So the three things that we'll kind of go through in the next couple examples. Normal PDF, we really don't use. PDF is a sort of like in a continuous distribution an equal to case, and that probability is 0, so it's kind of useless. But we do use it for graphing. Normal CDF is what we spend most of our time looking at. An inverse norm is when we'll get to that. It's kind of like when we're given a p-value and a probability, and we want to work out and find the z-score related to it. So a normal CDF is when we want a probability and we're given some sort of upper lower bound. So let's go back to here and let me pull up my calculator and let's go to the distributions. We actually did see this, we just didn't recognize that we saw this earlier. So we're going to go to distribution and we want norm CDF. Okay, and in the norm CDF, I'm sorry, let me get rid of all this other stuff here, so clear out the screen. Okay, so in the norm CDF, we're going to pick the distribution, and I want norm CDF, so I'm going to pick choice 2 for mine. And it's going to ask for lower upper. I want less than 220, which means that z-score that corresponds to that is that 1.33 we figured. So as far as the lower goes, I want this thing to go as low as it can. So that would be mathematically how we represent negative infinity. Upper, I want 1.33. And since we're looking, the z-scores are in standard normal curve, the mean would be 0, standard deviation would be 1. And so that's what we want to, it's lower bound, upper bound, mean, and standard deviation. So your calculator, you might just have to type that in. You might not have a fill in the blank like I do. And then I'm going to hit enter. And it's going to give me a probability of 0.9028. There we go. So that means the likelihood of it being smaller than 220 is about 90%, 90.8% of the time I would expect it to last less than the 220.